Okay, and hopefully Christophe already whet your appetite for how interesting of an inverse problem strong lensing image analysis is, which is great because our next speaker is Laurence Perreault-Levasseur. Laurence is the Canada Research Chair in Computational Cosmology in AI, an assistant professor at the University of Montreal, and an associate academic member of MILA. She's an expert in bringing machine learning techniques to strong lensing, which is what she's going to tell us about today.
All right, so thanks for the introduction. So yeah, I'm going to be talking more about strong lensing. And first, like full disclaimer, I am an astrophysicist, so this is really going to be like astrophysics, kind of like motivated. So I'm going to start by telling you a bit more context about what strong lensing is. So strong lensing is, like we saw in the previous talk, the formation of multiple images of some distant source due to the gravity of some intervening structure. So let's say that here we're on the Earth and there's two galaxies, one right behind the other one. So what happens is as the light rays of the background galaxy pass near the foreground galaxy, they get bent. And so they come to us from different angles. And so because of that, here on the Earth, we see multiple images of the same background galaxy. It's really similar to what happens when you look at a fish from the corner of a fish tank. If you've ever noticed, you see two images of the same fish. And then here I have Mr. Mango demonstrating that effect. So, whoops, right. So you see when you come to the corner of the tank, you see two images of the same fish, and it makes an image that's really similar to like an actual image of strong lensing that we see in the sky. So here there's two images of the same background quasar because of the deflection of its light rays by the intervening galaxy in orange. Here's another example of a strong lens. So here we see that the background galaxy gets sort of wrapped around the foreground galaxy and it makes arcs, and that's a really common feature of strong lensing. And the reason for that is the geometry of the lens. So you can actually reproduce that effect at home with a candle and a wine glass. So if you look at the flame of a wine glass through the foot of, the flame of a candle through the foot of a wine glass, you can see an image that really looks like an image of a strong lens, like this. And so in this analogy, the flame of the candle is the background galaxy that's getting distorted, and the foot of the wine glass is the foreground galaxy that's like causing the distortion. So this is a really cool party trick. But on top of that, like strong lensing is really interesting because it's a really interesting probe to do a lot of cool science. So first, that's the thing that I'm the most interested in strong lensing for, is because we can use it to study the foot of the wine glass. And that's because it's the mass of the matter that's in the lensing galaxy that's causing the distortion. So we can use this effect to map out how matter is distributed in the foot of the wine glass. And that's really useful to do things like map out the distribution of dark matter on subgalactic scales. And that's really interesting because it turns out that different dark matter models have widely different predictions for exactly those scales, so how they cluster on subgalactic scales. That could be a really important probe for informing us more about what the nature of dark matter is. Another thing that strong lens also, so the way that it works is like this. So it's a little bit as if you had like a droplet of water on top of the foot of the wine glass. What's going to happen is that it's going to cause an additional level of distortion. And because of that extra level of distortion, we can detect its presence, just like the way that here, like it's splitting the image of the flame of the candle in two, even though the water itself doesn't emit any light here. And we just infer it with our brain because we know that there's like an extra level of distortion. So we want to do exactly the same thing with strong lensing, but of course, in the case of strong lensing, the effect is a lot more subtle than this. Right, so another thing we can do with strong lensing is to use it to study the background source. And the reason for that is that it magnifies images. So that means that we can use it to study very distant galaxies that would otherwise be below our sensitivity or resolution limit. So we can use it to study, say, galaxy formation at really high redshift. And then the final thing we can use it for is to do cosmology. And so that's the way, basically we can use it to measure H0. And the way that this works is that when the different light rays pass around the foreground galaxy to get to us, they travel through different paths in space-time, and those paths have different lengths. So if the background source has some time variability, what's going to happen is that that's going to show up as a time delay from us, from our point of view on the Earth. And so because this probes really cosmological distances, it can be used to infer the value of H0. So now, depending on who you talk to these days, there might or might not be a problem with H0. So I'm not going to say anything about this, but one thing that's interesting is that this can be used as an independent probe to probe the value of H0. So it can really sort of help inform this debate because it has an independent set of systematics that could affect that measurement. All right. Okay, so this is a lot of cool science that we want to do with strong lensing, but how do we actually do that? Like, say, if I give you an image of a strong lens, how do I extract that science? And the way that this is done is through something called lensing analysis. So what we have to do is that from an image of a strong lens, we need to infer two things simultaneously. We need to infer the undistorted image of the background source, and we need to infer what is the shape of the foot of the wine glass, so the mass distribution in the lensing galaxy. So in terms, first in terms of an inverse problem, it has this shape where y is a vector of observed pixel of the observed image. So that's the data. X is a vector that contains the pixel values of the source parameters. So that's the undistorted image of the flame of the candle, the pixel value of that image. And then the reason why it's here is that these are actually linear parameters. So what that means is that if I want to get the distorted image, I can multiply those values by some lensing matrix here that encode the lensing distortion. But then the thing that makes this problem very difficult is that the parameters that describe how mass is distributed in the foot of the wine glass enter non-linearly in the construction of this lensing matrix A. So this is a problem that is both linear and nonlinear in the different parameters, and it's a vector of additive noise. So because of this, because it's a nonlinear inverse problem, it is non-convex, and so it's really a pain to sample with traditional methods. And the reason for that is that the shape of the likelihood is it has extremely wide modes that are extremely shallow and have no mass. And the only one mode that you do care about that has all the mass is extremely narrow. So it has basically no basin of attraction. So just trying to just land in there randomly is almost impossible. So it's really difficult to do this. All right. So it's a hard problem, but it's really interesting. And then in the coming decade, with LSST and Euclid and the Roman Space Telescope, we're going to be discovering lots of strong lenses. And so this is super interesting because we're going to have a lot of statistical powers to do the cool science that we want to do with strong lensing. The problem is, like I mentioned, it's really slow. So it takes about 3 days with traditional methods to do a lens model of a single lens, like a simple lens model. So if we scale that to the 170,000 strong lenses that are going to be discovered with LSST, it would take 1,400 years of a person's time to finish the analysis. Like if the person doesn't eat or sleep, so clearly this just does not scale. So that's why we need new analysis methods for this problem. And so what we've done a couple of years ago is that we've shown that this can be solved super easily with machine learning. We can just train a CNN to produce what are the parameters that describe how matter is distributed in the foot of the wine glass. So this is just a simple CNN. Here is the true parameters, here is the prediction of the network, and it does a pretty good job. But then the point is that this is 10 million times faster. So instead of taking 1,400 years, it would take 30 minutes on a laptop. So this looks promising. So since then, we've done a bunch of extension of this, and we've looked at different aspects of this. Another one that I want to mention is the fact that we're also interested in reconstructing the undistorted image of the background source. So the way that we've gone about doing this is that we've been thinking about this in more like a meta-learning kind of way. So we've trained this recurrent architecture to learn the process of optimization of the likelihood, so that and then we've trained it to always land to the right map solution in the end during training. So basically, it learns how to optimize. It learns the process of optimization of a class of likelihood, and then it produces the undistorted image of the background source. And one of the reasons why we like those kinds of methods is that we actually input the likelihood analytically, so it knows about the physical model that causes the distortion. So it's really well-motivated physics-informed method. And so the way that this does is like this, for this example. So this is the image I just showed. This is the truth we're trying to reconstruct. This is the machine learning reconstruction. And because, like I said, this is a linear inverse problem, we can actually reconstruct the undistorted image, we can reconstruct the undistorted image of the background source analytically, because the likelihood is Gaussian if we assume a Gaussian prior. And so this is what we get in this case. So clearly, just by eye, we see that machine learning does a lot better than analytical methods. So we can quantify how much better this does by looking at the coherence spectrum of the reconstruction. So this is the two-point correlation function of the reconstruction with the ground truth. So in blue is for the machine learning method, and in red is for traditional linear inversion methods. So we do see that on all scales, machine learning outperforms traditional methods. And the reason for this is, like I kind of quickly mentioned, is the prior that we're choosing. Because with linear inversion methods, because if we want to keep things tractable and analytical, we have to use a Gaussian prior, because that's the only thing we know how to invert analytically. And so it means that we're really not capturing our full knowledge of what we know galaxies look like. And that's why there was so much noise leaking in the reconstruction. Whereas with machine learning, the neural network can learn implicitly a prior distribution that's a lot more complex from its training data. So it has learned a prior distribution over what galaxies should look like. And that's what allows it to outperform traditional methods. This was really interesting because up to that point, we were mostly interested in machine learning for speed, but then we realized that actually maybe we can use this to do better than what's possible to do with traditional methods. So this isn't the case where, so we can play the game of like, all right, so machine learning is fast, it does better when everything's under control, but what happens out of distribution? So we know that they tend to be like pretty brittle. So we wanted to look at a really far out of distribution example. So we use text as the background source instead of a galaxy. And then, so we lens text like this is what we're trying to reconstruct. And so with linear inversion method, it does like, okay, as expected, but it has again the noise that leaks in the reconstruction. But then the machine learning method, surprisingly, one, does not break, which is great. And then second, still manages to do kind of better than the linear inversion method. So this is really cool. So it means it's robust to out of distribution examples. And the reason for this is that we actually give it the physical model of like the ray tracing simulation for how strong lensing is. That's so it knows about the physics of what we're trying to infer. So it makes it much more robust to out of distribution examples. Okay, so this is in the case though that we are assuming that we know what is the density inside the foot of the wine glass. So it's assuming that it's very simple. So it's like one galaxy that can be parameterized by a handful of parameters. So in reality, things are more complicated than that. So here there's a lot of galaxies in the lens. And like in particular, what we want to do is infer like the substructure distribution of dark matter in the lensing galaxy. We need a much more flexible model to represent this. So one thing we might want to do is to use a pixelated map of the 2D projected density in the lens and infer that simultaneously with the pixelated image of the background source. So we can do this using two of those models, like these recurrent models that I just talked about, that work together. So they jointly try to optimize the likelihood, the same likelihood. And then one of them is the same that I just talked about, that reconstructs the flame of the candle, and the other one reconstructs the foot of the wine glass. So this is my student, Alex Adams, who's done this work. And these are examples of what he gets. So here, I just want to stress that like, this is the lensing galaxy here, and this is the reconstruction. And so it really manages to reconstruct extremely complex density distributions that would be extremely difficult to do with parametric models. And in fact, here I cannot compare with like traditional methods because I cannot model those lenses with traditional methods. It's just not possible. So this is something that would just be completely intractable to compare with. And so this looks really promising to be the kinds of method that you want to be using to infer complex mass distributions in the foot of the wine glass. But the problem is that everything that I talked about so far is giving me a point estimate. So if you're a scientist and an astrophysicist, what you want to see is more something like this. Like you want to see a posterior with samples. And so because basically what you want to know is what's the uncertainty over the quantities that you're inferring, because that's where the science is. And so, so over the past years, we've gone on a very long journey of exploring different methods that we could use to use machine learning, but also be able to quantify the uncertainties. We've looked at Bayesian neural networks, simulation-based inference, NREs, like all that kind of good stuff. But the thing is that it's very tricky because here we're interested in doing precision science. So we want to have statistical guarantees, and we also want to have some form of interpretability. Because if I just had this CNN or a neural network that told me, okay, temperature of dark matter is like 10 keV, like you should not believe me if I tell you that this is this because my like plus or minus, even if it's plus minus 2, for example, because you like as scientists, we're going to want to know where does that information come from. And if I'm using, say, an NRE to directly infer from data this value with uncertainties, I don't have access to, say, posterior samples that are consistent with the data that I observed because I've marginalized over all those parameters. So I cannot tell you, okay, the signal comes from a very large population of low mass subhalos, or it comes from very few high mass subhalos. Like I have lost access to that information because it's been implicitly marginalized over. And so it looks like if we want to have So if you want to have interpretability and access to these ways to interrogate what is it that the machine learning methods are learning, we also need to develop those high dimensional posterior inference methods. And so it looks like we're really going to have to tackle the hard problem of doing high dimensional inference. So there's a bunch of things that are hard about this. But so to start to get going about this, one thing that is worth thinking about is that what allowed the REM to do better, which is the place where we did high dimensional inference that kind of worked, is that it could learn a prior distribution implicitly that was much more complex than what we could do analytically. So one way forward would be, okay, so if I want to actually produce samples, maybe I want to learn this prior distribution explicitly and then be able to sample it and then do my inference like this. But then the other thing that's hard is like, if I have this high dimensional prior that's very complex, how do I actually sample my posterior in really high dimensions, so like millions of dimensions, which is also a hard problem. Okay, so let's take things one at a time. What if I want to learn my prior distribution explicitly? So in my case, this is images of galaxies, undisordered image of galaxies. So can I learn how to sample this just from examples of galaxies that I have around me in the universe? So can I, can I model the density of those galaxies directly? So let's say that here, so this is really high dimensional, obviously, because every pixel is one dimension, but I can represent this in 2D. So here, every point is a galaxy. Like this, but of course it would be like at least 10,000 dimensional in reality. Okay, so if I want to model the density of this space where galaxies lie, so then what I would want to do is something like train a neural network to maximize the likelihood of my data, and I could do that with, say, by minimizing the KL divergence. But this is really hard to do in practice. And the reason for that is that the density is a normalized probability function and so probability density function. And so what that means is that the value of the density at one point depends on what's going on everywhere else in the space. So it has no local information in it. And because of that, it's really hard for a neural network to learn. So it's possible in kind of lower dimensional settings, but in like 10,000s to millions of dimensions, it's really, really difficult. But actually, it turns out that to learn to sample from this space, the only thing that I need is the score, which is the derivative of the log probability that I want to sample. And then the score is basically like a vector field. So at every point in this space, there's a little vector that's pointing me towards the higher density region. And because it's the derivative, now it only has local information in the space. So this is something that is much easier to learn for a neural network. So there's some hope that if I can learn the score within the neural network, then I use that to sample my probability distribution. So I don't have time to go I don't have time to go into details, but so this is some work that my student Alex Adam has done. And so you can learn this with score matching. The score, so you can train your network to learn the score. And then once you have done that, you can use Langevin sampling to basically sample one realization of noise, that just a random Gaussian field, and solve a reverse MSD to produce one sample from your distribution. That's a new sample. So this is something that you can do with diffusion models. And so you can produce new galaxies. That's sort of pretty cool. So my postdoc, Cornerstone, he's collected this data set of real galaxies, and he's trained a diffusion model on those. And there's a bunch of those galaxies here that are real, and there's a bunch that are not, and I don't know which one is which. But you can go to this website and generate more fake galaxies. It's pretty entertaining. It really looks realistic. All right, so this is a way to generate more galaxies. So these are samples from my prior. This is not what I want. I don't want random galaxies. I want the one galaxy that's sitting behind my one. So I want samples from my posterior. So if I want to sample my posterior, I need the score of my posterior. But the good thing is that I know Bayes' theorem, so I can split the score of my posterior between the score of my likelihood and the score of my prior. And then the score of the normalization constant just drops out because it's a constant. So the evidence just drops out because it's a constant with respect to parameters of interest. So this is what I just learned with my score-based prior. And then the score of the likelihood, I don't know exactly what it is, but if I assume that my node is Gaussian, and I know my physical model, and in the case of like background galaxies, it's a linear inverse model, I can actually use some approximations if I'm very careful to write this approximately, and it's actually a pretty good approximation. So I have the two terms that I need to be able to get samples out of my posterior. So I can do this here. So here what I'm showing is the background galaxy that I'm trying to reconstruct. Here's like the model, and here's like these are the posterior samples as a function of how much noise I add in my mock image. So if there's very little noise in my mock image, I have a lot of information in my likelihood, so it's extremely constraining. So what's gonna happen is that there's very little variability in my posterior samples because the likelihood has so much information, there's almost no uncertainty. But as I increase the amount of noise, there's more and more variability between the different posterior samples because there's more uncertainty. And in strong lensing, the central part of the background galaxy is magnified more because that's the part that forms the arc. And so there's a lot more information about that part. And so it's reconstructed much more consistently across the different samples, like the center of the background galaxy. But the outskirts are almost like lost in the noise here. And so the outskirts of the galaxy, the information is lost by the likelihood. So the information gets filled in by the galaxy prior, basically. And so it sort of gives posterior samples that have more uncertainties in the outskirts, but that are very like certain about what's going on in the center of the background galaxy. And in the case where there's just noise and all the information has been lost by the likelihood, like there's no information, then I just get a random prior sample. That's just a random galaxy. And then if I want to say, okay, with what certainty do I reconstruct this feature in my background galaxy, I can count, like I can look at how many samples I have that feature and say with how many sigma I can say that this feature exists or not, for example. Okay, so this, I can play the same game of going out of distribution to see how robust this is going to be. So I can look at the number 7 as my background galaxy. I wanted to have 42, but back in those days, that wasn't so good. So now like we should just remake this. But yeah, so this is 7, this is my background source, this is my lens model, and then this is my different mock data as a function of how much noise I add to them, and these are the posterior reconstructions. So if I add very low noise, again, there's a lot of information in my likelihood, and that's the part that's analytic. So the 7 is going to get reconstructed with a lot of certainty, even if it's really far out of distribution from my prior. But then as I start adding more and more noise, we see that the central part of the 7 gets reconstructed consistently across the samples, but the outskirts get filled in by prior information, which is galaxy information. So it's going to get sort of smoothly interpolated between like the part that has information from the likelihood, the middle of the 7, and galaxy samples in the outskirts. And then in the case where there's no information in the likelihood, then I just get random galaxy samples because that's what my prior says this should be. So this really works as I would expect this to work. It makes sense. It's intuitive. But then like the real question is like, how do I quantify if like those samples I'm showing you are actual posterior samples or the sample from another distribution? So this is the question of accuracy. Like, how do I know when I'm sampling something if they're actually samples from the right distribution? So typically this is done with coverage tests. And so the way that this works is if I repeat my experiments multiple times, and I look at a given interval in my posterior, I can count how many times the true value falls inside versus outside of that interval. And so ideally what you want is the number of times it falls inside to be equal to the fraction of the total probability volume that there is inside that interval. So typically, so let's say that I have like the 1 sigma confidence interval, I want my ground truth to fall 68% of the time inside that interval. And that has to be true for like all the different intervals. So this is typically done with the region that has the highest density, like the highest density region, like what I'm showing here. But the problem with this is that it requires knowing what the density is, but it doesn't scale really well to really high dimensional spaces. And then the other thing is that this is not a sufficient condition for calibration. Like let's say that in this case here, I always predict to the like right of the ground truth. I could completely pass this coverage test because the distribution is symmetric, but I'm still going to be biased because I'm always predicting to the right of the peak, right? So this is a necessary condition for calibration, but it's not a sufficient condition for calibration. So what we've done with my postdoc, Pablo, is that we've designed a new coverage test that basically has a new way of generating the intervals that basically relies on generating random points to cut different regions of the probability density. And then instead of looking at the density of the points of the posterior samples, it looks at the distance between the samples. So it only relies on calculating distances. So it scales really well in high dimensional spaces. So you can use it like the L2 distance, the L1, whatever distance you like, you can use as long as like consistent. And so it scales to really high dimensional spaces. It's really fast. And the nice thing is that we've proven a theorem that says that this test is a necessary and sufficient condition for calibration. So if you pass the test, you're guaranteed that you're calibrated. And this is installable, so you can just go into it. So in the interest of time, I'm going to skip the explanation of exactly how this works, but you can ask me how it works after. So these are just examples of like coverage plots. So this is in the case where it's calibrated compared with like high density region. Here's like different cases we can detect when it's overconfident, underconfident. And then the cool thing that I wanted to show here is that in the case where the highest density region would not detect that it's a biased thing, like the case where I'm always predicting on the right, then TARP manages to detect that it's biased. So we've run that on the galaxy samples that I showed before. And in the case where we're not careful with the likelihood approximation that I talked about, then we get the bias curve. But then once we incorporate this correction that I did not explain exactly what it is, but that is there, then we manage to get calibrated samples. So this is like pretty cool because it's a guarantee. It's a good guarantee that we're doing the right thing with our inference. All right. So this looks like we're really in business to start applying this to data. But then, like I said, I've assumed that my likelihood was Gaussian, and this is what real data looks like. This is not, there's no signal in there, this is noise. And noise is messy, like there's a bunch of cosmic rays, and this is JWST noise, so there's a lot of stripy, super highly correlated noise. So this is not Gaussian. So I think, what can you do? I don't know what my likelihood is in this case, right? But then I already said that if I want to learn, I can learn a distribution and I can sample from it with score-based models. So I could train a score-based model to learn my noise distribution. So I can do that, and I can produce new samples of noise. So this is fake noise. So I can sample new real distributions that looks like HST noise, or that looks like JWST noise. So I could use that in two ways. I can use this in like a simulation-based inference framework to produce really realistic simulation of noise that I'm going to add to my data to have really super realistic simulations. So that's one way. The other way is that I can use this to do explicit inference as well as my likelihood model. So the way that this works is like this. So the distribution that I've learned is the distribution of the noise Q. So the score is the gradient of the log of that distribution. But the distribution Q is basically the distribution, it's my noise distribution, but it's also the same thing as my likelihood, because my likelihood is the function of my data minus my model, which is exactly the thing that should be noise. And so I've actually learned my likelihood distribution. So I can plug this in my Langevin sampling algorithm here. But then the problem is that when I want to do Langevin sampling, I need the score with respect to the parameters of interest, not the parameters of the data pixels, basically. So, but what I can do is that I can just use the chain rule to get the gradient of my physical model here. And if I have written my physical model in a differentiable way, I get this for free. And so I can just use this to sample my likelihood, my posterior, sorry. So this is a comparison of a simulated strong lens injected in real Hubble Space Telescope noise. And so if I assume that the likelihood here was Gaussian, I would get the blue contours, which are all like super biased. And if I use this like slick likelihood to sample the parameters of the strong lens, and I get the unbiased gray contours. So it's really possible to do unbiased inference using this method with complex non-Gaussian noise model. So this is the chart curve that shows that it's actually unbiased over multiple examples. All right. Okay, so I'm going to go quickly over this. So this is an example. Now we can do a lot of linear inverse problems, so it's super cool. So we can look at PSF decomposition. So the Hubble Space Telescope, when it takes an image, actually it dithers. So it takes 4 different images of the same place by shifting by sub-pixel values. And then to remove cosmic rays, it kind of averages all of the 4 through like the Drizzle algorithm. And so that kind of like averages the noise and removes the cosmic rays. And so it makes the noise look more Gaussian. But doing this removes a lot of information. But now that we have a way to characterize our non-Gaussian noise, we can actually analyze jointly the 4 different images to get all the information out of those images. So if we do this with the framework that I just talked about, and we can get a reconstruction of what the underlying like actual galaxy looks like, which looks like this, and then we can look at residuals, and they all look completely consistent with noise. So that means I've extracted all the information from my data. So that's pretty cool. And then I can just do a bunch of things like looking, okay, so how much do the features that I reconstruct depend on the prior that I use? Like if I use real galaxies versus simulated galaxies as my prior. What if I use different like diffusion schemes? How does that influence my posterior? So this is what we've done here. And so that like for this image here, we always get this kind of like spiral arm in all the samples, and they're kind of constantly reconstructed on the median of all my posterior samples. So this looks like this is a consistent feature of my reconstructions. And then we can go, like after we've done all of that, we can go to DWST that has also observed the same galaxy and see if this is real or not. And it's real. So we can get JWST quality data with just HST if we just extract all the information that's already there in the data. So we can do this. So these are, yes, I'm going to skip over. We can do the same thing of going out of distribution using a galaxy prior to infer protoplanetary disks. So they kind of have the same geometry. So this also works. But then, okay, so I wanted to, I'm out of time, right? I'm going positive now, so it means, okay, I have like 5 minutes-ish, right? Okay, good. So I can, so all right, so then like the thing is I want to use the garbage test to know if I'm in distribution or not. So that's, and then typically I'm going to get things like this, that like some curves that are kind of on the diagonal, some curves are kind of off, but this is the pass or fail test, right? So it's kind of hard to know when is it that I'm good enough with this. So it would be really nice to have a metric that tells me a number, like if you're this good, or this is the probability that you're in distribution versus not in distribution. So this is another thing that we've done with my postdoc Pablo recently. It's called PQ mass. So it's basically exactly that. So it's looking at the probability that two sets of samples come from the same underlying distribution. And so the way that this works is basically by tessellating the space. It's all based on this, is the same idea as like the way that TARC was phased. So if I have just one region, and I have a bunch of samples, so I cut my space, I just get one region. If I assume that, like, let's say I know the underlying probability density, then the probability that I've drawn this many samples in my region versus out is going to be given by the binomial distributions. For the red sample, it's going to be the binomial distribution. For the blue sample, it's going to be the binomial distribution too, which is a different number of samples I have. So I could do that with one region. And I can also tessellate my whole space with Voronoi tessellation to get all my space tessellated region with like a bunch of Voronoi cells. And then in that case, the probability that the samples for, say, the blue points are going to be distributed the way that they are is going to be given by the multinomial distribution. And same thing with the red. So what I can do is I can do a bunch of definitions, and then I can just say, okay, so if I assume that those two sets of samples come from the same underlying distribution, what is the probability that I'm going to have drawn those specific realization? So we can define basically a statistics like this. It's like basically a cat for statistics, and then we can show that given any sampling distribution or like any generative model, if those two sets of samples are generated from the same distribution, then that statistics that I've just defined have to follow a cascade distribution with like the number of regions that I have minus 1 degrees of freedom. So what that means is that I can just like, I can work in like, hundreds of dimensions, like with some toy models. And I can say if I have two sets of samples from this prediction of that like 100-dimensional distribution, if I repeat that tessellation multiple times, then it's going to follow a cascade distribution. So that works with like toy examples that are relatively like low dimensional. But also if I look say at MNIST digits, I can look at if I split MNIST in two, can I detect that they are in distribution with respect to each other or not? And yes, like they do follow a cascade distribution. These are just null tests. But then I can use this to do cool things like detect if I have a mode that's missing in my distribution, for example. So I said I have this like 100-dimensional like mixture of Gaussians here, and I want to know if I'm missing samples from one of the modes, then what's going to happen is that the peak of my cascade distribution between the two are going to be shifted compared to the optimal values. This is as a function of the number of modes that I'm missing. It's basically going higher and higher, meaning that it's detecting like more and more confidently that the two sets of samples are not coming from the same underlying distribution. But because it only relies on like distances between points and tessellating the space, I can also scale that to really high dimensional spaces, say like images. And I can detect how well my diffusion model is training compared with like a test set. So here what we've done is we have two different runs of training a VAE and two different runs of training a diffusion model over MNIST. And then we can track this PQ mass value, this like statistics over as a function of the training epoch. So initially all the models are kind of bad. They're really far from the optimal value that they should have. the peak of the cascade distribution. But then as a function of training, you see the values went down. So for the two VAEs, they kind of saturated pretty high. So they don't really manage to get in distribution because they blur images. We know that VAEs do that. But then the diffusion model gets kind of close and they get pretty good. So we have like an objective metric to quantify how good are the samples that I'm generating with my diffusion model. Or my generative model that I'm training. All right, so I'm gonna just talk very briefly about this, and then I'm gonna be done, and you can ask me about this more. Okay, so now we have like diffusion models, they're gonna be our prior, but the training data that I have for those diffusion models, it's corrupted data because it's galaxies from like low redshift, say, and so they have noise, they have PSF effects in them. Maybe I'm using low redshift galaxies that have high resolution, but then actually I want to infer high redshift galaxies. So maybe they're kind of like, they don't have the same morphology at all because there's some redshift evolution with galaxies. Another thing I can say, well, I don't want to have this effect, so I'm going to look at simulations for galaxies, but simulations are imperfect, so they could also be added to the distribution. And so the question is, should I worry about this or not? Is this something that I should care about? The fact that my prior is actually going to be out of distribution because I've used some data to train that prior, and that data was out of distribution. So basically the thing we would want to do is to get, right, so yeah, we want to learn this like population level prior articulated. That's like the correct thing we'd like to do, but that's really hard because then we get a distribution over our diffusion models, and like maybe that's going to be tractable, but like initially we want to do that a bit more. We want to be a bit more conservative in our goals. So we're just going to do empirical base and basically try to find a diffusion model that maximizes the likelihood of the data. So the one parameter of the diffusion model that maximizes the likelihood of the data. And we're going to do this iteratively. So basically burn one round of observations to do some inference. If it's out of distribution with the initial prior, I can train a new diffusion model on those and then keep on going like that until I have converged to like the prior that I want. So yes, you can ask me more about this. Do you want me to stop or do you want me to keep on going? I have like just 2-3 slides, but yeah, maybe I can just say, turns out that it works and we can learn, we can discover new modes in the data, we can forget modes that are spurious, and we can also discover, we can, from an initial prior of red noisy like elliptical galaxies, we can learn that elliptical galaxies exist. So we can definitely learn things that are out of distribution. All right, so I'm going to stop here and hope that I have convinced you that it is not only worth like pursuing very fast implicit inference approaches, but it's also really worth pushing the development of explicit likelihood approach to get interpretability. And in the long run, if we really want to be doing precision science with machine learning, we really want to make sure that both these methods all give the same answer. So thank
you. No, it's a great talk. Question.
Hi, thanks for the talk. It's super interesting. My question is about the uncertainty quantification on the source image. I thought the results were super impressive, but from my understanding of how you formulated the problem, there's sort of like more unknowns than just the source image, right? So you're like simultaneously trying to
yes, that is not what we have done yet. And what I've shown, I'm assuming that like some higher intelligence has come down to Earth and given me the parameters of the lensing galaxy. So this is the assumption I'm working on right now.
Yeah, okay, cool. Yeah, I just have like a more of a big picture question maybe. Yeah. So like ideally what you really want if you had like the perfect model is you want to maybe recover a joint distribution right, on the source image and the lens parameters. But
100%.
I mean, even then, like you probably can't capture the lens completely with a parametric model because there's like submasses and then there's like external convergence and all that stuff. So I guess the main question is like, what do you think is the path forward? And then on top of that, do you think that given like the crazy difficult nature of the problem that maybe ultimately we probably would need more observables than just the lens image?
So, I mean, the obvious next step is to learn jointly like a prior distribution over the mass in the lens, like a pixelated 2D density map and a prior over background sources and do the joint inference with diffusion over both these things. So this is like, it was hard to do high dimensional inference in the linear problem over the background source, but now we want to do both. And the problem is that the lens is, it's nonlinear, so it's more complex. The reason why we haven't done it yet is because of that approximation that I kind of skimmed over in the likelihood. And things, if you just naively say, I'm going to use the same approximation with my nonlinear problem and just trust that things are fine, things are not fine. It does not work. So you need to be a lot smarter about the way that you go about writing down that likelihood at high temperature. And so this is where we're putting our efforts right now. So stay tuned. Results are coming.
Thank you.
Other questions, I think it's on.
Thank you. Okay, so how well do these learning-based reconstruction techniques work for, say, massive group lenses or galaxy cluster lenses?
So for cluster lensing, it's a lot harder. And it's like, in principle, there's nothing harder. The thing that's hard is that GPU have a finite size memory. And so it's just a matter of like the number of pixels you have in your image. So like in a strong lens, if you want to have like a high resolution like background source, you could do 256 by 256 pixels. And that's, I mean, that's kind of high dimensional, but it's tractable. But like for a cluster scale lens, like the image is a lot high, like you just, the data has a lot of pixels and the background source needs also to have a lot of pixels. And so because of that, just the, like the size of the diffusion model you need in terms of like gigs of memory is very large. And so it's more difficult because of that reason. So like if you wanted to apply the same kind of models to that scale, I think something along the lines of latent diffusion would be definitely like the way to go, because then you can do diffusion over lower dimensional latent spaces.
And it's not harder because the deflector dark matter distribution is more complex or not SIS or whatever?
So, well, it depends how, like, okay, so I'm talking about reconstructing the background source, because as I said, doing the lens is much more difficult. So you could do the same way that people do like cluster lensing right now. You can just evaluate where you have your SIEs and then model the handful of parameters that you have. Or like your NFW profiles, for example, like you just pin down where they are and you can just do that inference as a set of, you know, parameters that is not like millions of dimensions, but you know, you could go to like hundreds or something, couple hundreds for like the mass distribution and then do the source. And you can do those jointly, that's possible. But it's not like fully non-parametric, like it's not fully pixelated jointly.
Other questions? Yeah.
Yeah, thank you very much for this interesting talk. So I come from a very different domain in astronomy, where I'm also working on inverse problems, but in X-ray and gamma ray astronomy. And now you've put all this effort into training these nice diffusion priors. And I think this raises a bit the question, because they're, to a certain degree, they're universal.
Yes.
And I think this raises a bit the question of something like image foundation models for astronomy. And I was wondering whether you're aware of any efforts in that regard or related, whether the models that you've created are publicly available.
Yes, they are. The answer is yes, they are. So Alex has a really nice score package that's available. Oh yeah, that's my last slide actually that I didn't go through yet, this slide. So this really nice group of people that are my students in postdoc, they have put this super cool simulation package for like strong lensing. So it's all differentiable and it has all the possible effects that you might need in a simulation for strong lensing. So that's like, you can go pip install it and like go have fun. But also like all the background source priors for galaxies, they're also publicly available. And Alex, who's in the middle here, he has a GitHub repo that's called like score-based models. And this is all also, like it has all his code for training diffusion models, all his architecture and all of that is there. And it has also the trained network in there.
Okay, thank you very much.
And yes, about foundation models, yeah, we're kind of like, I mean, that's kind of like what we did, like we kind of use our like galaxy prior as a foundation model, but I don't like foundation model because it's like the word that doesn't mean anything anymore. But yeah, so it's a little bit like a foundation model because we can use it to reconstruct protoplanetary disks, even though, because they have kind of the same shape and feature and it's the prior. And so, and it works very well. So it works way better than things like the clean algorithm or like MPOL, like all those other algorithms that you could have that don't give you uncertainties and it have assumptions about the background sources that are wrong, say like point sources as opposed to like extended objects.
Final question for Laurence?
All right, if not, let's thank our speaker again.